All right. So things are going to get math heavy here in a second. But conceptually, that's what we're talking about. When we're talking about activation energy and temperature, that's in that exponential part. That's just how many of the atoms, because both of those affect the amount of energy that all of the atoms and molecules have, and how often they'll have enough energy, or how many of them have enough energy to reach a reaction. The frequency factor is where we get the number of sort of approaches towards that activation barrier. So getting into the correct orientation or colliding with the right other molecules in order to react. So which of these statements best explains why reaction rates generally increase with increasing temperature? A. The biggest factor for temperature is that as temperature increases, a greater fraction of molecules have enough thermal energy to get over the barrier. B is incorrect, partially because that's not always the case. So for some reactions, it might increase the rate of collisions, so it'll have some effect, but the larger effect is having enough energy to actually get over the barrier. Doesn't affect the pre-exponential factor that much. For C, molecules decompose into their constituent atoms, which then can form new bonds. It's not the case, is kind of a oversimplification of what's happening. It's kind of adjacent to the truth. So what is the activation? I guess, why is there this activation energy barrier? Where does that energy go?
Into breaking bonds.
Into breaking bonds. So it is true that the activation energy is required because we have to break bonds in order to form new bonds. The reason that C is incorrect is because it's talking about this as if our molecules need to completely break apart so that their constituent atoms can then reform into the new molecules. But that's ignoring the fact that we also have to have the correct collision or the correct situation for the reaction to happen. All right, so we can take our Arrhenius factor and we can rearrange it. This is not doing an integral. We're just rearranging the factor to give us the form of a line. Right, our y equals mx plus b, y, and then the temperature here is x. The slope is the activation energy divided by r. And then, oops, plus b, the intercept is the natural log of a, which would be that pre-exponential factor, or the frequency factor. And a lot of times A is relatively small compared to other things going on and gets ignored. Another important thing to note is that R here is in joules. Oh, actually, let me write out the number. 8.314 joules per mole Kelvin. It's in units of joules. So this is the same. This is the gas law constant, but it's just different units. So if we have enough data, we can plot all of our different reaction rates, or rate constants in this case, right? We're plotting rate constants against temperature. Temperature is the x, rate constant's the y. And if we plot those, we'll get a straight line plotting the natural log of the rate constant versus 1 over temperature. And now we can use this equation of the straight line. Let me do it like this to figure out information about the reaction. And the y here is representing the natural log of k. The negative 1.12 times 10 to the 4 is the activation energy over R. X is 1 over T plus the natural log of A. And I think it asks us to find the activation energy. No, frequency factor and activation energy. So frequency factor is A, activation energy is E sub A. So frequency factor is a little bit easier. They're both pretty easy from this. But there is some interpretation that we have to do because on our graph, A here, right, here this 26.8, that's the natural log of A. So we could, if you wanted to, set this up as an equation. Natural log of A is equal to 26.8. And then make those things the power of the natural base. So the natural log of A, or E raised to the natural log of A is just going to be A. And then E to the 26.8, be 4.356. Times 10 to the 11. I think technically that's only 1 sig fig because of the decimal. So how do we find the activation energy? Do the same with the slope. And the key here is that the slope, so just like this 26.8 didn't represent just A, it represents the natural log of A. The slope here is not just the activation energy, it's the negative activation energy divided by R. So we can do the same thing and set up another equation where it's negative EA over R equals negative 1.12 times 10 to the 4. And we solve for the activation energy. And R is 8.314. So really this is going to be negative 1.12 e to the 4 times 8.314 negative. Make that negative, so the negative cancels. And so the activation energy is not negative. 9311.6.8. And the units here are going to be joules. And then the units for A, well, it's a little bit weird because when you actually calculate K, and we do this equation of, I should write it on here so it's in the video, right? K equals A times E to the EA over R and T. The units of activation energy are joules per mole over R, which is joules per mole Kelvin, and temperature is in Kelvin, and all of those units cancel out. But K has units. The units of K depend on really whatever the order of the reaction is. And those units come from A, our frequency factor. And in this case, we need to get that from really our rate constant, which was given as part of the data that would have been graphed. Otherwise, there's not another way to figure out, just from what we were given here, what the order of the reaction is. So our rate constant is inverse molar, inverse seconds. So this would be molar to the -1, seconds to the -1. Oh, and it didn't ask for this in Kelvin, but oftentimes activation energy is in, not Kelvin, kilojoules and not joules. But so really the key takeaway from this is that the slope gives you, or the equation of the line gives you the natural log of A and negative activation energy over R, and you have to solve for those to get activation energy and the pre-exponential factor. Aside from that, it's algebra. All right, so another way we can use this, let's see, so we're using the results of the previous problem to predict the rate constant now at a new temperature. And so if we want to predict the rate constant at a new temperature, because the activation energy is constant, we can just set K equal to the Arrhenius equation, negative AA over RT. K is equal to that times E raised to the just plug in all those numbers now. Oh, don't forget the negative. And I do want to point out, I converted from kilojoules to joules for the activation energy. Because R is in joules. 8.314 joules per mole Kelvin, so activation energy has to be in joules. Let me go to this. So this would be 4.36 e to the 11 times natural base, the negative 93,100 divided by 8.314 divided by 298. Yeah.
Why are you dividing by 298?
Because it's easier than doing parentheses and then multiplying the 2 on the bottom. Yeah, so I'm just kind of like changing the order of operations, which you can do. If you don't like that, just do parentheses. Make sure that it does. Well, yeah, because if I don't do parentheses here, so I did the 93,100 divided by 8.314. If I do times 298, it'll do this division first and then multiply the whole thing by 298. When really I'm taking this, divide it by that, and divide it by this. So, okay. as long as I typed everything in right. 0, 2, 3, 4, 2, 0, 8, 9. Oh, 8, and that's same units. Or you could say 2 point. Oh, this was nice. They reduced everything down to 2 sig fig or 3 sig figs. So yeah, I think hopefully you feel the same. The math on any of these is not too difficult, but it's probably knowing how to use the equations, like which equation to use where. So Verissimo's lecture worksheets, do those problems. I'll assign a variety of problems from this section. I'll probably pool it so it'll give you like a random, it'll draw from a random pool. Because that's what's going to take practice. Being able to identify when. And a lot of that is like, what are you given? What are you trying to find? Looking at the available equations. And I did look at, on Alex, if you want an explanation for a problem, it is on the buttons on the right. It's the one with the little glasses. Any other questions? All right. Hopefully this gives you like a library of references. I'll try and get this posted today too. Oh, I haven't been adding chapters. I'm gonna add chapters. All right, so another form of the same equation. This is the 2-point form of the Arrhenius equation. So if you've got limited data or graphing isn't possible, then you can use this just with 2 different points because we have some constants. So this can be used a lot of different ways. You could be solving for K, you could be solving for T, you could be solving for the activation energy. The thing that's important to keep straight is that whatever you put on top, you put the corresponding temperature first in the 1 over T2 minus 1 over T1. It doesn't matter if it's the larger one first or the smaller one first. The negative will end up canceling. So we would use this in a situation like this where we've only got rate constants at 2 different temperatures and we want to find the activation energy. So we've got, and I'm going to highlight these to make it easier to track. Let's see, can I pick colorblind friendly colors? So we got 700, or rate constant at 701 K. We might even want to say, let's just call this T1. 701 K, K1 is 2.57. T2 is 895. K2 is 567. And then natural log of K2, K1 negative EA over R, T2 is 1 over T1. In my mind, it helps to remember, like there's so many other places where this happens, but it's like final minus initial. So 2 minus 1, put the 2 first, put the 1 second. But again, the order doesn't actually matter. Or whether or not I picked these numbers as T1 and K1 or T2 and K2 doesn't matter. We're just assigning them so it's easier to keep track of. So this is going to be 567 over 2.57. it's negative EA over R, which we could fill in, 8.314. 1 over T2, which is 895, minus 1 over T1, which is 701. And now it's kind of up to you how you want to solve this. Because we're back to, it's just algebra. I would say if you have no idea where to start, just start calculating and simplifying things that you can. So this is 5.39645. And then this is negative 0.123309215. You could, of course, rearrange the whole thing ahead of time if you wanted. Sometimes easier to do when you just have variables. And now I just got to get EA by itself. I can actually make these negatives into positives. Be careful for, just because it's a mistake that I've made, this is being divided, so it's got to be multiplied. It's one of those things that should be obvious, but it's easy to miss. Whereas the other number, the 0.000309, that's divided. So you should end up with, nope, I missed a 0. There you go. $145,096. That's going to be in joules. Or joules per mole. Oh yeah, this one's sinister. Yeah, why is it 2?
Because of the 2 decimals in the ln,
So technically when we take the natural log, this, since the numbers going into the natural log have 3 sig figs each, this would keep 3 sig figs here.
Okay.
Then this is why I say, because in doing this earlier,
After the decimal.
yeah, because when you take the natural log of something, decimals are significant.
3 sig figs.
But this is supposed to be 2, as indicated by the solution up there. And it's because if you actually do this division and then this division, and then you subtract them, right? When you do subtraction, you keep the smallest number of decimal places. This goes from being like 0.000, oh, wait, yeah, because there's 3 zeros here. It goes from being like 0.00 something and 0.00 something for this to 0.000. So if I keep the same number of decimal places, I lose 1 sig fig there. That's a really nitpicky sig fig thing.
Not that nitpicky.
No. Sig figs are a little more relaxed in Chem 2 because there are a lot of places where, like if you type that all into your calculator, you're never going to see that. And it's going to take extra time that I don't think is really necessary to actually type that out. The hard thing then is like, well, what is the hard and fast rule that you should follow for sig figs? I'll say this, at least never have more sig figs than your starting numbers. You should never have more sig figs than your starting numbers. It should be the same or less. That's tempting. Maybe make that an extra credit kind of thing. If you catch those really small sig figs. Yeah, that's a good question though, because the answer here is 1.5. Why is that 1.5? Well, because of those sig figs. So do that. If you want to check it for yourself, actually divide those, write out the math, count the number of decimal places. When you subtract, you end up with one less. The only thing we would do here after this was convert it into kilojoules. So you get 145.09, and we know now that those aren't necessary. We're going to do the next problem also. So whenever you're working with natural logs and exponents, the rounding error becomes a lot worse. So we're going to use this number in the next problem. So while the correct final answer for this problem would be 1.5 times 10 to the 2 kilojoules per mole, that's not the number that we want to use in the next problem. And I will show you why. So now we've got, okay, use the results from example 15.8, and the given rate constant of the reaction at either of the two temperatures, doesn't matter which one you pick, and predict the rate constant for this reaction at 525 Kelvin. As the math gets more complex, there are more and more ways to do this. One way that you could do this, so maybe call this method 1, is if we think about, well, we've got K equals, we got the Arrhenius equation, so negative E over A over RT. We can fill in a lot of this. We found the activation energy. We have the temperature given. So that's E, that's T. The only thing we need is A in order to find the rate constant at the new temperature, right, K. Well, we could find A because we have rate constants and temperatures and now activation energy for our other two temperatures. So we could use that to solve for A. A is a constant for this reaction. So if I solve for A, we could plug in for one of our other values, like the 2.57 equals A e to the 145.096 7289 divided by 8.314. Oh, and that was at 701? Yeah. And then solve that for A. Plug that into here. Then we plug in 525. We plug in our activation energy in kilojoules, or in joules, not kilojoules. And then we can solve for K. Bless you. The other way we could do it, and probably the way intended by the book here, is we can use the natural log of K2, the 2-point Arrhenius equation. Right, because I have all of the information for one, temperature. I have K, I have the temperatures. And now I have activation energy, so I can plug all of that in and solve for one of those Ks. Wait, we got time. So let's solve it out this way. I'm going to do something on this side. So this natural log, it's the natural log of K2 divided by K1. One of the rules of logs is that if I have division happening inside of a natural log, I can separate that and turn it into subtraction. So the natural log of K2 minus the natural log of K1. And then, actually, I'll start plugging numbers in here. So I'm going to solve for K2 because that's the positive one. And I'm going to use 2.57 from the previous problem. That's one of the Ks. I'm going to use my activation energy of, in joules, 145,096.7289 joules per mole over 8.314 joules per mole Kelvin. 1 over temperature. So K2 is what I'm solving for. K2 will also be my new temperature. 525 minus 1 over 701. So a lot of math on that right side, but I can do negative 145,096 divided by 8.314 times, and in parentheses, 1 divided by minus 1 divided by 701. So now I've got 3460877. That's enough. So now I can add the natural log of 2.57 to both sides. Natural log K2 and then E raised to that number. So that K2 is equal to 0.000609921. It's probably a good time to emphasize, while it may make sense while you're watching me do it, it is beyond important. The only thing that's important is that you can do it without having seen it done right away. Right? So rather than following along or looking at a series of steps and saying, oh, that makes sense, you need to be able to do that yourself, starting from a blank question, which is why things like the lecture worksheets or the homework are so important, because the only way you know if you know it is if you do it. And then when you get stuck, you have something to reference. Okay, so I was talking about how rounding errors, super important. I used the whole number. Hello? It's really annoying. And I'm still off by a little bit. So I don't know where they rounded this number at doing this calculation, but even using the whole thing, it's slightly different. So that is, to a certain extent, to be expected. I'm gonna have to look at the Alex problems to see how they mitigate this. Well, let me show you on these other slides. Going through, doing a practice run. Oh yeah. I do a lot more of the math just on the calculator. If you don't, or if you round, if you use with the correct sig figs from the previous problem, 1.5, you get 0.00046, which is a lot farther off than just the 6.0. So by losing all of those decimals, you lose a lot of that. Now you don't need to keep as many as I did. If you know where the sig figs end, so there we had 2 sig figs, keep like 3 or 4 digits past that, and that's probably enough to mitigate the rounding error. The more that you can do in your calculator, though, the less that you actually have to write those numbers and retype them into your calculator. Or if you have a calculator like this, you can save numbers as variables, which is always useful. Are there any questions? It's a lot of math, and we got to go through it fast. But that's why office hours exist. If you do have other questions, yeah, okay. It's like an okay place to stop. Other questions, I have office hours right now from 11 to 12, and then from 1 to 2. I'll be in my office. We've got a whiteboard, you can ask questions. Yeah.